Alright, so picking up with our polynomial function, zeros of polynomials. Remember, if we have a complex root or an imaginary solution, the conjugate pair must also exist. When we're finding the equation given the roots, we're going to write it as a product, specifically x minus each number that's given. And remember, if an imaginary root is given, then I'm also going to include the conjugate pair. For example, here it says find a fourth degree polynomial function f of x with real coefficients that has -1, 2, and I as zeros. So what I was saying a moment ago was, if that's one of my zeros, think of bringing the 1 over so that it's set equal to 0. This is one of my binomials that I'm going to want to FOIL out. So if it helps you to do it this way, set it up like this. Bring the 2 over so that way it's set equal to 0. And then we also have I. But remember, when we have x equals I, then I'm going to have x minus I equals 0. So that's one of my binomials. But remember, the conjugate pairs exist. So it's not just x minus I, it's also going to be x plus I. So a complete list of our binomials is going to be x plus 1, x minus 2, x minus I, x plus I. And all of this is going to be f of x equals. And now what I'm going to do at this point is FOIL it out. I particularly like to begin with my imaginary roots, my conjugate pairs. Why? Because when I FOIL them out, the middle terms I know are going to reduce. So all I have to do is just first and last. So that's going to be x squared minus 1 I squared. And I squared, I know that's -1. So this is what I get here. So in this one, I end up with x squared plus 1. The next thing I want to do is FOIL out these terms over here. So here I'm going to get x squared. My next term, my middle terms, it's going to be -2x and plus positive 1x. So minus x. And then my last term is going to be -2. So the very last step to finding our polynomial function would just be to multiply this binomial by this trinomial. So let's rewrite it to make sure that we know which way to go. I personally like to multiply my binomial to my trinomial. So x squared times x squared is x to the 4th. Then I have minus x cubed minus 2x squared positive x squared minus x minus 2. So all I did was distribute to all 3 terms and then distribute to all 3 terms. Now I'm just going to combine like terms. So we end up with x to the 4th power minus x cubed minus x squared minus x minus 2. And this is the 4th degree polynomial that has the given zeros that were given to us in the given. Now we're going to talk about Descartes' rule. Descartes is a rule of signs. I think it's best to just show an example of it. What we're going to do is we're going to count the number of sign changes with the given, and then we're going to put in a negative for x, and then we're going to count the number of sign changes for the new polynomial function. Let me show you an example. Let's take a look here. Here at the top, from here to here, there's a sign change. It went from positive to negative. Do you guys agree? From here to here, no change. From here to here, there's another change. So that's 2 so far. From here to here, no change. And then last, I have x to -3. That's another sign change. So a total of 3 sign changes. So according to Descartes' rule, there are going to be 3 sign changes. So therefore, I have 3 possible positive rational roots. So remember when we listed all possible rational roots, the plus minus 1, plus minus 2, etc. I had a whole list of positive and negative ones. This helps us narrow it down. So here I'm being told that there are going to be 3 from the list that are going to be positive solutions. So it's going to help us out. However, the rule also states that I have to subtract an even integer from whatever I get, because it could be that I have 3 or that many minus an even number. So what number is even that's less than 3? 2. So it could be that I have 3 or 1. That's the rule. 3 or 1 possible positive rational roots. Okay? Let's take a look at another example. Let's count the sign changes in the second one. From here to here, do I have any sign changes? No. From here to here, do I have one? Here to here? Here to here? Here? Okay, so there was just a total of 2 sign changes, right? So according to Descartes' rule, I have 2, subtract an even integer that's good, 2 or 0. According to Descartes' rule, I could have 2 possible positive rational roots or 0. Alright, let's take a look at our last example here. I have no change here, I have 1 change here, and no change here. So according to Descartes' rule, there's 1 possible positive rational root. Got it? Let's just make sure that we understand it. Remember, in order to determine the possible number of positive and negatives, the positive ones we do first. So here I'm going to count the number of sign changes. Here, this should say minus and minus. I only have 1. Therefore, according to Descartes' rule, there's 1 possible positive rational root. Got it? Now we're moving on to the negatives. In order to determine how many negative rational roots we could have, all I would do is substitute a negative in for x. Does the negative affect even exponents? No. It's only changing the odd ones, right? Okay, once I change them, that's what this is showing, then I count the sign changes. This should say plus 5x minus 6. Okay, how many changes do I have now? 2. Okay, and remember, according to Descartes' rule, I also have to subtract the even integer, so it's 2 or 0. Good. Alright, so now let's take a look at this example. This example says, for the given function, how many positive and negative zeros are there? So we're going to use Descartes' rule to help us, and we're going to determine what are the zeros of the function after we determine that. So let's count the number of sign changes for our possible positive roots. Okay, how many sign changes do we have in the given? Okay, here's 1, here's 2. So according to Descartes' rule, it's 2 or 0. Good. Now we're going to do the negatives. In order to do the negatives, we're going to plug in a negative x. So I'm going to just rewrite my function really quickly. My negative x cubed switches. My second term doesn't, because negative x squared is x squared. This one switches. And now I'm going to count the number of sign changes here. How many do I have here? 1. So according to Descartes' rule, I have 1 negative solution. Now, what I want to do is, in order to find the zeros, I'm going to go back. Remember, we talked about listing all possible rational roots, where I put p over q. I'm going to create that list. So here, my factors for my constant 3 is going to be plus minus 1, plus minus 3. Over the factors of our leading coefficient, which is 1. Anything over 1 is itself, so this is a thorough list. Now I'm going to randomly pick numbers, but I'm going to use Descartes' rule to help me out. I'm going to narrow it down. I know I'm going to have possibly 2 rational roots that are positive, so I'm going to start with the positive ones for synthetic division. I'm going to start with positive 3. You could pick 1 if you want, whichever number you like the best, start there. So my number is completely random. I'm going to use synthetic division starting with 3. So now I have my synthetic division set up, and I'm going to go ahead and divide. Bring down your first term. 3 times 1, 3. Add them, we get 0. Multiply 3 times 0, 0. Add them, negative 1. Multiply 3 times negative 1, negative 3. And we got lucky. So our remainder is 0. That means that 3 is a 0. Now that I know that 3 is a 0, I can depress this from our synthetic division. Remember, we started to the third power, therefore we're moving on to the second power. Okay, now that I have that, I'm going to go ahead and solve for x, add 1 to both sides. Take the square root of both sides. What do I get? Good. So a complete solution set is going to be -1, 1, and 3 for the given. So we just found all our zeros. Okay. And I just want you to topically know about lower and upper bounds. We'll explore this a little bit more when we talk about the intermediate value theorem later on. So right now this is just kind of like getting you ready for it. What this is saying, if the number that you're dividing by, if it's positive, and when you do synthetic division in your answer, all of them are positive or 0, then we consider that an upper bound solution. If when you're dividing by a negative value and the solutions to the synthetic division alternate signs or 0, can be counted as an alternating sign, doesn't matter, then it's considered a lower bound. Let's take a look at an example. Alright, so here's our last example. It says, using synthetic division to verify the upper and lower bounds of the real zeros of f. We're just verifying, and I hate when it does this. It switched my signs again. This should say x cubed plus 3x squared minus 2x plus 1. So now I'm just going to verify. Remember, upper bound, dividing by positive, good, so that's meeting criteria 1. And I'm going to go ahead and do synthetic division. 1, 3, -2, 1. Bring down your first term. Multiply them, add them, multiply them, add them, multiply them, add them. Because all the solutions here are positive, that means this is an upper bound. It is an upper bound solution. And I will elaborate on what that means as we proceed in talking about other topics with polynomial functions. Let's take a look at B. So B has -4, it's meeting criteria 2, it is negative, it is less than 0, and now I'm going to do synthetic division. So for my synthetic division, my setup is going to be 1, 3, -2, and 1. Bring down your first term, multiply them, add them, multiply them, add them, multiply them. That should be, no, that's negative, that's right. And then here, do you see that your signs are alternating here in the solutions? That does mean it is a lower bound solution. It is a lower bound solution. And again, I'll clarify what this means when we start talking about different concepts with polynomials, but this is to get you started with your homework.